So you got introduced to the pre-quiz. So usually what I'll do is I'll give you pre-quizzes to get rid of like the just the factoids, get those out there. And then I make you do, so you watch the video, take notes. And the pre-quiz is just to make sure you watch the video. The questions I ask are not intended to be tough. If you get all three right, 100%. If you miss one, still 100%. If you miss two, 33%. If you miss all of them, on 0%. Okay, so you have one grace question that you can miss, freebie. Okay, the whole point is watch the video, pay attention. Sound good? Okay, so that is how we roll with pre-quizzes. Okay. All right, get your notes out. We've got some ground to cover today. So I believe I left you with that slide there. Clock reading. That's not going to work. Okay. So, time duration. This is what you didn't see yesterday or 2 days ago. Time duration. This is a change in clock reading. So, change in clock reading is final clock reading minus initial clock reading. So a lot of textbooks will just use T. I think that breeds some confusion for subtle things. The delta T, so if I ask for how long did something go running, or what was, for how much time did this, that you're looking for delta T. Often when we do this, we have a stopwatch and our initial clock reading is 0, but not always. Okay, so that's delta T. Needed to kill that. All right, so today we're going to talk about ratios and velocity. Okay. So you go to a gas station, fill out 14.7 gallons, and it costs you $58.40. What does this ratio communicate then? Okay, dollars per gallon. Is there another way to say that same thing without using the word per? We kind of throw around per pretty loosely. Like, we know how to, I can put this into a calculator. The calculator is going to give me 3.97. Okay. But check this out. This is the same thing as that, right? But if I'm faithful with the units, this is the important part. Units in physics are like really, really important. This is see how that is working? Okay. So what's another way I can say this without saying per? Price per gallon. It's how much each gallon of gasoline costs. Is how much money there is for every 1 gallon of gasoline. Okay with that? We're familiar with this. This is what's posted on all signs, gas station signs, right? Okay. It's not a really happy price, but it's not something that's unusual. Okay. But what happens if I flip that ratio? I didn't break anything mathematically. It's just not something we're used to seeing. What does this communicate? If I plug this into a calculator, I would get 0.252. Jackson, yeah. What is that? Good. Yes. Yep. So I've got gallons on top, dollars on bottom. This is I can get how much gas I can get for every $1. Okay. Good with that? Okay. So when you divide anything, you are finding the ratio. Okay. So like the rest of your life, if you're paying attention to the units, that's going to go really well for you trying to figure stuff out. Okay. So in general, a ratio communicates how much of the numerator there is for every 1 unit of the denominator. How much of the numerator there is for every 1 unit of the denominator. Good there? So, looking at this equation, what are the units so is everybody good with meters per second? But what I'm trying to show you is this. Displacement is in meters, time duration is in seconds, so the unit for velocity is meters per second. You okay with that? You can do that for any equation the rest of your life. Figure out what the units are based upon your equation. Okay? All right, so in the video, I talked about how it's an average velocity. Why do I need to specify average velocity? Why couldn't I just do like velocity? Like, why do I need to like specify average? For like a trip versus like the actual or the instantaneous velocity. Have a conversation. Okay. What could happen in a trip? Could slow down, could speed up, it could pass somebody, it could hit a stop sign. Okay, so if velocity changes, okay, so when could I use this equation and find my actual velocity? Like when would this be a valid approach to find my instantaneous or my actual velocity? Like what would I have to be doing in my car in order to have that be the actual thing? Elena. Right. If velocity is constant. If your velocity is constant, then your average velocity is your velocity. If you in class, if you got an 80% and 80% and 80% on a test, on tests, your average test average is 80%, which also communicates your actual score is what you got because you like were consistent on your test average. Does that make sense? Okay. So we can use this accurately to figure out if velocity is constant. So I'll give you this little disclaimer. In this class, for this chapter, we're going to assume that the velocity is constant during the times we're looking at it. Okay. So we're just going to camp out on this equation for this chapter. Next chapter, we'll get into when velocity changes. Okay? Tell your neighbor what you think.
Oh wait, never mind.
Okay. What do you say? Got some A's and I got some B's. All right. So your velocity is equal to displacement over time duration. So final position minus initial position over final clock reading minus initial clock reading. Okay. Your final position was 10 yards. Your initial position was 40. Your initial clock reading will be 0 because we started our stopwatch at 0. And the final clock reading is 5 seconds. Often, okay, just quick little timeout here. Often I'm just going to write delta t is 5 seconds. I won't go through this. Okay. This is helpful if we were like, kind of like what you were doing on your lab, the first lab where you're like having to read the stopwatch on the fly. Okay. So you get negative 30 over 5 b, negative 6 yards per second. Good with that? Okay. Now, how does the sign, the direction of velocity compare to the sign displacement of, sign of displacement? Is it the same? Is it the opposite? It depends. Is it possible for displacement to be negative? We just did that. Is it possible for a a time duration to be negative? If that was the case, he would be going back in time. It can happen in the movies. It really messes things up, but not in physics class. Okay, so delta t will always be positive. So whatever the sign of this is, that will always be the sign of velocity. Okay, so velocity will always have the same sign as displacement. Okay, it tells you which way you're going. So if you're walking this way, you have a positive displacement, you have a positive velocity. If you're walking this way, you have a negative displacement and you have a negative velocity. The sign of displacement and velocity will tell you which way you are moving. You okay with that? One of the nice things with physics is there are statements I can make always statements and never statements, and they're valid. Okay? Have a conversation.
There are three of them with no numbers.
Correct answer is B. Okay? The magnitude of velocity is the absolute value. Actually, the magnitude of anything is the absolute value. It's the number, it's the how much. In this case, it's the how fast. Okay? Um, what do we call the magnitude of velocity? What name do we give that? Speed. Good with that? Okay. So influence, don't be influenced or influence others. Keep it in your head. We'll talk about it momentarily. Tell your neighbor what you think.
That's what I said. I said G. That's, yeah. Oh. Thank you.
What do you say? Correct answer is D. Dangerous dinosaurs. Okay? They're going in opposite directions, and the absolute value is greater for the mom. Okay? Do not fall into the trap of, like in math class, you would say positive 4 is greater than a negative 7. That is true in math. We're talking about the magnitude of that for speed. 7 is greater, has a higher on your speedometer than 4. They're just moving in opposite directions. Good? Okay. Check out that one. That's like way at the beginning. I like backtracked a lot. Well, have a conversation.
That's why I feel weird, but I think it's. I was super.
Displacement is just the total.
Yeah.
So then it's probably.
Correct answer is D. Um, so this is if you're just moving in the positive direction versus this could be in the negative direction. All right. So if in a problem, okay, a tourist is fishing, looks up, sees a bear 26 meters away. Deciding to make a break for it, he bolts, goes 4 meters a second towards the car. Exact same time, the bear takes off chasing the tourist. How far, what's the maximum distance that the tourist can be away from the car so the bear reaches him just as the he reaches the car? Okay. All right, real quick. Notice I did not specify which way is the positive direction. So my recommendation would be make the way they're moving positive. That way, they're not changing directions. They're going in the positive direction. Okay. So you can flip flop between distance and displacement. You can flip flop between speed and velocity. You don't need to make a distinction between the two for scenarios where they're going in the same direction of the positive, and like they're not changing direction. Does that make sense? Okay. So, all right, here we go. Step one, draw a picture. Okay, it doesn't have to be elaborate. Um, Bear doesn't look like it needs food, but all right. So we got 26 meters away. We got the bear going at 6 meters per second. Tourist going at 4 meters per second. Car is somewhere over here. We don't know. Everybody be able to reproduce that? Like, do pull all that stuff out. Okay. So, okay, really big picture idea strategy. If you have more than one object moving independently of each other, you need a set of variables and an equation for each object. Okay, so we need the bear's velocity, we need the bear's displacement, we need the bear's time. And the only equation that we have at this point, which is kind of convenient for us, is velocity of the bear is equal to the velocity of the bear's displacement over the bear's time. I need the same stuff for the tourist. And I have the same, I only have this equation to work with, but I need a separate equation for the tourist. Okay. So see if you can figure out, fill in as much as you can for those variables. Okay, so we have 6 meters per second, we have 4 meters per second. This is what I'm looking for. Like this is the tourist displacement. Those are the obvious ones. You okay with that? Is the bear's displacement 26? How can I communicate the bear's displacement?
26 plus the tourist displacement.
Okay, so the bear has to run 26 meters in addition to what the tourist has to, sorry, you're right there, to the, what the tourist has to run. Does that make sense? All right, that's a good connection. Okay, do I have anything that represents time? Or like communicate, have anything? I don't. Like, ugh, stop. Put that off the side there. All right. So if I don't know anything value-wise, who's running, what object's running for more time, the bear or the tourist? Or are they running the same? Ready, set, go. Stop. Ready, go. Stop. Who's running for a longer period of time? Not distance, but time. Go. Stop. Same. Does that make sense? Okay. So, though I don't know it, I don't know the value, I don't know the number, I do know that they're the same. That's a nice thing. So, here we go. I've got bear, 6 meters per second is equal to displacement, 26 meters plus the displacement of the tourist over some amount of time, which I don't need to make a distinction between the bear and the tourist because they're the same. And then I have an equation for the tourist, 4 meters per second is equal to displacement of the tourist over a time. How many unknowns do I have? I have 2. How many equations do I need to solve for 2 unknowns? 2. Guess what? 1, 2. Boom. Okay. Up until this point, this is physics. This is taking a scenario and putting math to it. Beyond this, this is math class. I do not care how you get to the answer. There's lots of different options. Okay, you got 2 unknowns, 2 equations, substitution, elimination. like set them equal to each other, whatever you want to do. Lots of different ways. Whatever hits you first. Okay. Um, I'll just demonstrate it. So what I'm going to do for me, I'm going to set both equal to time and then put them equal to each other because time's the same. Again, there are a lot of different options you can do here. So I'm going to multiply both sides by delta t. Okay. So I got 4 times delta t is equal to delta x. And I'm going to drop the, yeah, okay. And then I'm going to divide by 4 on both sides. So I've got delta t is equal to delta x over 4. I'm going to do the exact same thing over here, but I'm going to skip. I'm going to not show all my work. What I get is I'm going to bring delta t over here and 6 on the other below. So I got 26 plus delta x over 6. Okay. Because they're equal, both equal to time, which are the same, I'm going to set those equal to each other. I'm done using different colors of ink. Okay, we're just so at this point I'm going to cross multiply.
Do you need like meters per second still on the bottom?
Good question. I don't.
You don't?
You could if you wanted to, but
So you can just use the number.
yeah, yeah. Okay. So I'm going to cross multiply here. So I'm going to bring it up here. So I got 4 times 26 plus delta x is equal to 6 times delta x. So this is 104 plus 4 times delta x. This is 2 delta x, 104. I get 52 meters. Good, Aiden? Awesome, dude. Okay. There is an intuitive way to do this. I'm not going to teach it. I'll tell you how to do that, but I'm not going to teach that because if you catch this intuitive way, this is going to fall apart next chapter. So I'm not going to put a whole lot of emphasis on this. This way is tried and true. I would recommend going this route. Okay. The conceptual way, or okay, the intuitive way to do it is like, okay, so the bear runs 20 or 2 meters per second faster than the tourist. So every second that goes on, he gains 2 meters. The bear is 26 meters behind the tourist, so it would take 13 seconds for the bear to make up that 26-meter difference. If the tourist is running for 13 seconds, he can run 52 meters. That would be the intuitive route. If that didn't hit you, just let that pass on by. That's fine. Okay? So, tried and true. In summary, if you have more than one thing moving independently, you need a list of variables and an equation for each object. And then you start figuring out the connections between the two. Good with that? Okay. All right. right, so you're jogging for 20 minutes and then walking for 20 minutes. What is your average velocity? Okay. Um, so, correct answer is 3 meters a second. There's a lot of work. I'm going to jump to this next problem. Okay. So, this is a similar type of problem. You're going 100 miles. For the first 50, you're going 80 miles an hour. For this last 50 miles, you're going 60 miles an hour. What is your average speed? Assuming no pit stops. Okay. So, um, yes, there's only one object moving, but there's two different motions. So what you're going to do is you're going to do, just like the bear and the tourist, you're going to break this up. So you have the fast velocity for the fast part of the trip, displacement for the fast part of the trip, and the time for the fast part of the trip. And you're going to have an equation for the fast part of the trip. Then you're going to have a list of variables for the slow part. Okay. The, the difference for this compared to the bear and the tourist is you're going to have a total. So your average velocity is your total displacement over your total time. Meaning that we've got your your displacement of your fast plus your displacement of your slow over the time of your fast plus the time of your slow. You all right with that? Okay. So do you see the setup there? What I'm doing? And see how that's similar to the bear and the tourist. Even though I have one object, I have two separate motions. The 80 miles an hour and then the 60 miles an hour. Okay. So see if you can fill in as much stuff as you can. Okay. How we doing? Okay. I know my total displacement is 100 miles. I know this is going 50 miles at 60 miles an hour, and this is at 50 miles at 80 miles an hour, but I don't know anything about time. Could I find time, though? Yeah. Check it out. I mean, I'm like, boom, 80, and I'm going 50 time. So time is 50 over 80, whatever that is. Okay. And same thing over here. This is 60. It's 50 miles over time. So my time is 50 over 60. You can, I mean, I would just do decimals. Yeah, 100% reduce. So this is 0.625. And this is 0.83. So 0.625 plus 0.833. Okay, before we find out the number, because we can all do that on a calculator, I'm going to ask a question to you. Here, in this, the answer was 3 meters a second. Okay, the reason why it was 3 meters a second was just the average of the 4 and the 2 is because they were traveling for equal amounts of time. So you can just straight up find the average. In this problem, were they traveling for equal amounts of time? No, they're traveling for equal amount of distance. Which one took longer? Which 50-mile an hour trek took longer? The one where you're going faster or the one you're moving slower? Slower. So your average velocity is going to be less than 70 because you spent more time traveling 60 miles an hour than you did traveling 80 miles an hour. Okay? And so when we do this, 100 divided by whatever that is, we find that to be 68.59 miles an hour. Good with that? Okay? So in summary, if you have more than one object or more more than one stage in your problem, separate it out. You need variables in an equation for each stage or object. And then if you're looking for the average overall, you've got that thing. Okay? Got that worksheet due tomorrow. Woo!